Hello, I'm Zhu Wei, a student from Hangzhou University, and I will introduce my paper at the SMTPD below. Below, I will start with 4 parts: the introduction, SMTPD dataset, popularity prediction, and the specific details of the experiment. In recent years, with the advancement of Internet communication technology, social media has gradually emerged and has affected all aspects of human life. Social media popularity prediction has greatly application potential in content optimization, online advertising, digital marketing, search recommendation, smart fashion, and other fields. This figure shows the content selections and the popularity trends of SMTPD. The left figure shows 4 parts of content contained in a sample. The right figure depicts a box plot of daily popularity scores, illustrating the changes in popularity distribution at different time points. Over time, the distribution always shows a declining pattern. As shown in the table, the social media popularity datasets that have been published or mentioned in recent years are listed. However, existing datasets and related studies have obvious limitations, such as insufficient multimodal data, limited language diversity, and most importantly, the lack of consistent prediction timeline. As shown in the right figure of PPT on the previous page, the popularity distribution changes over time, and predictions made at irregular intervals will reduce accuracy and bring challenges to practical application. In addition, effective popularity prediction requires integrating information about the multimodal contact and propagation process of social media to capture the dynamic trend of popularity. This important aspect is missing in most current prediction work. In this paper, in response to the above shortcomings of existing datasets, the contributions of our work can be summarized as follows. First, to address the problem of the missing temporal information in social media popularity stores, we observed more than 282K multilingual samples posted on mainstream social media for 30 days. We call these samples SMTPD. Second, based on the existing methods, we innovated on the sections of feature extractors and the contribution of temporal regression components and proposed a baseline model that can predict temporal probability across multiple language. Third, explore the popularity distribution and the correlations between popularity in different periods. On this basis, we found the importance of early popularity for popularity prediction tasks and point out that accurately prediction early popularity is the key to predicting popularity. Social multimedia has become the most popular form of media in the world today. However, as mentioned earlier, this data without arranged publishing time without show inconsistent popularity distribution. Therefore, SMTPD closely follows YouTube with more than 282K samples and focuses on the evolution of the popularity of these samples. Over time, we collected more than 402K raw data samples. Especially, we removed samples that were not clouded on certain days or detected within 30 days. We used 3 sigma rules to feed out potential outliers. The left figure describes the statistics of different languages in SMTPD. Since there are more than 90 languages, the table only shows the part of statistics. The right figures describe the basic static of all samples in SMTPD. Compared with SMTD, due to the multilingual environment, we use characters to describe the average length of the header. The figure above shows a data sample of subset. Longer text context is omitted in our definition, but the ID remains unchanged. Many definitions of plurality were derived from previous work. We use Koestler's plurality scores transformation because it normalized the distribution of field counts to a suitable plurality score distribution. It can be expressed as the above formula, where P is the plurality score, V is the number of fields of the sample, and D is the corresponding numbers of the day after the post was published. As shown in the right figure, the histogram of the field counts shows an extremely long tail distribution, which may not be suitable as the prediction target. Obviously, the distribution of the probability score logic has become more reasonable. Multimodal feature fusion is the mainstream method among probability prediction methods today. Since metrics such as fields and probability were usually based on the cover frame that viewers see before clicking play, we use the cover frame as the main visual content. This approach balances the impact of probability and the copyright. The text context of the article plays a vital role in media dissemination and user engagement. We examine several core elements, including technical, title, description, and text, as well as user IDs from profile multimedia. Numerical attributes also often used as factors to improve prediction accuracy. In this study, we examined key attributes including field durations, number of followers of the uploaded, and the number of posted of the uploaded. In addition, we added several metrics such as title length, count of custom text, and the description length to further enrich the feature set and support the prediction robustness. This PPT shows SMTPD statistics based on categories. The upper left figure shows the statistical distribution of classified content, and the lower left figure shows the average probability of samples in each category. The right figure illustrates the distribution and the probability diversion between title languages. In this study, the temporal prediction framework based on multimodal features is shown in the figure above. The framework is mainly divided into two parts: multimodal feature extractions and temporal probability score regression. This framework is designed to adapt to multilingual temporal prediction tasks under time arrangement. The prediction target is set to the probability of the sample, which corresponds to the temporal probability within 30 days after the sample is released. The upper level processes visual, textual, numerical, and categorical features and inputs them into a multi-layer perception. The NLP output is connected and fed to the lower LSTM layer for regression. The output of each LSTM unit is passed through another NLP. In these sections, various experimental results and detailed descriptions are then presented, including evaluation on the SMTPD datasets, the proposed baseline, multimodal features, and early probability. We first measure three recently proposed SOTA probability prediction methods on SMTPD. Since these methods are designed with the setting of SMPD in mind, we make some modifications to make them suitable for training and testing on our SMTPD. Given that our SMTPD datasets consist of temporal probability scores, we restrict these methods to only predict a single probability score on day 30. To mitigate random biases, we use 5-fold cross-validation for evaluation. The above table shows the minimum performance difference between flows, confirming that SMTPD contains rich data under balanced sample distribution. It is obvious that for single output prediction of probability on days 7, 40, and 30 with the SMTPD, the GBDT-based data method outperforms the deep learning methods, and in terms of both NAE and SRC through its powerful calibrates the regression ability. It is nothing that our method achieved the best result after adding EP, while the NAE of the other three models increases with the increase of the prediction horizon. In contrast, the NAE of our model started to decrease after day 14. In addition, there are two interesting observations. First, all methods achieve higher SRC on SMTPD than on SMPD, which may be because SMPD lacks specific time points and it is difficult to accurately predict time related to probability trends when probability decreases, and their NAE performance will definitely decrease as the NAE value increases above 0.16. In addition, the layer probability range and the standard deviations between SMTPD samples also increase the difficulty of prediction. If you evaluate the performance of the proposed baseline on SMTPD, as shown in the table, the proposed baseline surpasses the second best method by 0.798 lower NAE and 0.109 higher SRC. This huge improvement is mainly brought by the early probability. Without the assistance of EP, the performance of baseline drops sharply compared with the existing method. Obtaining more parallel temporal information from back propagations allows for more accurate prediction of probability in subsequent time steps. These comparisons clearly show that EP plays a crucial role in probability prediction, and accurately predicting the post-day probability is key to predicting future probability. Our results, as demonstrated by the NAE and the SRC curves of natural EP and our model predictions, highlight the model's ability to leverage EP to improve accuracy. Our baseline model can well optimize NAE and obtain better SRC performance than the natural EP curve. Therefore, the proposed baseline model can effectively leverage EP to achieve better prediction accuracy. This demonstrates the prediction effort of our model and shows the key role of EP for probability prediction. This concludes our presentation. Thank you for listening.